we're going to start a new chapter today, chapter 3. So we finished chapter 2. Uh, we're going to talk about the polynomial and the rational functions in this chapter. And this is probably the most complicated chapter or most challenging chapter in this whole course. The essential problem here is to solve a polynomial equation. That's what we want to discuss. How do you solve a polynomial equation with degree more than 2? We know how to solve linear equations. We know how to solve quadratic equations in different ways, but how about the cubic equations and higher degree equations? And we have to discuss different topics in this chapter for that purpose. So let me just start from the very basic background about remainder and the factor. Okay, so the first section in this chapter is the remainder theorem and the factor theorem. Okay, so let me just discuss division of polynomials to start. Suppose you want to divide two polynomials. How do you do that? It will be the same way as you do division of numbers. And that's called non-division. You just make the table like this. So we want to divide the 6x cubed minus 16x squared plus 23x minus 5 divided by 3x minus 2. So I'm going to put this dividend at the top. 6x cubed minus 16x squared plus 23x minus 5 inside, and the 3x minus 2 outside on the left, like this. And then the next thing is to divide 6x cubed by 3x. If you divide 6x cubed by 3x, you're going to get 2x squared. Put 2x squared on the top, and then multiply 2x squared with 3x minus 2. You're going to get the 6x cubed minus 4x squared, right? If you distribute 2x squared. And then you're going to subtract that from the dividend. So, and then, you change the sign of everything. So you got negative 6x cubed plus 4x squared. So, and then 6x cubed cancels, and then you are left with the negative 12x squared. And then you move down the next term in the dividend, 23x. All right. So you got negative 12x squared plus 23x. And then you're going to divide the negative 12x squared by 3x. Okay, this is always the way to do it. And then you're going to get the negative 4x. And then you multiply negative 4x by 3x minus 2. So you're going to get the 12x squared plus 8x. All right, if you distribute negative 4x. And then you're going to subtract that from the dividend. So that becomes positive 12x squared minus 8x. And then you just combine those, so you get a negative 12x squared and 12x squared cancel. And 3x minus 8x, you get 50x. And then you move down negative 5. So you got 15x minus 5. And then you divide the 15x by 3x. And you get a 5. So I need to put 5 on the top line. So there's a table here. I don't know why I missed that. So then you plus 5 on the top after negative 4x. I'm going to correct it in the slides. So 5 times 3x minus 3, 15x minus 10, and then you subtract for that from the dividend. So that becomes 15x plus 10, and then you just combine So 15x and negative 15x cancel, and the negative 5 and plus 10, you get positive 5. So in the quotient on the top, you got 2x squared minus 4x plus 5, which I missed here. And then you have the last number 5 at the bottom. That's called the remainder. So you can write the answer of this quotient as 2x squared minus 4x plus 5, which I also missed in here, plus 5 over 3x minus 2. Okay, the first 5 is on the quotient, and the other 5 is in the remainder, all right? So that's how you do the non-division, and that's pretty the same thing, pretty much the same when you do division of numbers. Any questions for this example? No question. Let's move to the next page. Okay, so in some cases we can do the division of polynomials in a quick way, and that's called the synthetic division. But synthetic division, it can be used only for division by x minus c. Okay, if you divide the polynomial by x minus c, then you can use synthetic division, where c is any number, not just the real number, but also complex numbers actually. And the rule for synthetic division is add down, multiply up. So let's do one example of division by synthetic division. We want to find the result of x to the fourth minus 4x squared plus 7 plus 15 over x plus 4. We're going to do a synthetic division. We can also do the division by non-division as we did in the previous example, but it turns out is a little quick and shorter if you use synthetic division. Okay, so what you do, you're going to put all the coefficients of the dividend, the numerator. So that's the first coefficient for x to the fourth is 1, and the coefficient for the next term is 0. You know, the next term is x cubed, but there's no x cubed in this problem, so the coefficient is 0. And the next coefficient for x squared is negative 4, and the next coefficient for x is 7, and at the end we get 15 as the constant. And then you're going to put negative 4 out on the left, like this, and draw a diagram or table like this. You put negative 4, not positive 4, because you need to write the divisor x plus 4 as x minus negative 4. Then this negative 4 will be the c we talked about. You remember we talked about x minus c, so c will be 4 in this case. And then we can start do the synthetic division. So add down, multiply up. So the first number 1, you just move it down. Okay, so you get 1 here, and then you multiply negative 4 with this 1, so you get negative 4, and you put up below the 0. Okay, so then you add 0 with negative 4, you get negative 4. So that's add down, multiply up, add down. So again, you multiply this negative 4 with the negative 4 on the upper left. We had at the beginning. So negative 4 times negative 4 is 16. So you put this 16 up below negative 4. So that's multiply up. And then 4 plus 16, you go to 12. So that's add down again. And then you multiply this 12 by the negative 4 on the upper left. So you get negative 48. So that's multiply up again. And then you 7 with negative 48, you get negative 41. That's add down again. Now you multiply negative 41 with negative 4 on the upper left. So you get the positive 164 and put under 15. So multiply up and then add 15 with 164 equals 179. So that's add down again. So then we get out, and you can write an answer using those numbers at the bottom row. And the last number on the bottom row 179 is the remainder for this division. So you can do add 179 over x plus 4 for the last term in the result, and then the other numbers, the other four numbers, gives you the coefficients of the quotient. Okay, the quotient starts from x cubed. Okay, you got x4 on the top as the highest power, and they divide by x plus 4. So you're gonna get x cubed as the has the power. Any questions? So then the highest power is x cubed in the quotient, and the coefficient for x cubed is 1. And the next term, x squared, and the coefficient is negative 4. And the next term, x, the coefficient is 12. And then the next term is negative 41 without x. So and the quotient will be x cubed minus 4x squared plus 12x minus 41. And again, you add the remainder 179 over x plus 4 at the end. So that's the syntactic division and how you write the answer from syntactic division. Okay. Any questions? No question. Let's just go to the next page. Okay. Let's talk about the remainder theorem. The remainder theorem says the polynomial p is divided by x minus c. Then the remainder equals p of c. So what does it mean by that? That means, if you want to find the remainder of a quotient px over x minus c, you can do it by plugging c for x in this polynomial p. Okay, so let's just do one example to show that. So we want to divide the polynomial p of x equal to 2x cubed plus 3x squared plus 2x 2 by x plus 2 and x minus 12 using syntactic division. So we need to do two syntactic divisions, one by x plus 2 and one by x minus 1/2. So let's just do it one by one. So let's just do the syntactic division of p and by x plus 2. So again, you put the coefficients of the dividend, 2x cubed plus 3x squared plus 2x minus 2. So you just put the 2, 3, 2, negative 2, right? And then you put the negative 2 outside on the left with some vertical bar to separate this negative 2 with the coefficients of the dividend. The negative 2 comes from x plus 2. If you rewrite x plus 2 as x minus negative 2, okay, then c is negative 2. You just put negative 2 on the left. And then you do a syntactic division. So the first step is move down the 2 at the first place. All right. And then you multiply this 2 by the negative 2 on the upper left. You get negative 4. And then you add to a negative 4, you get negative 1. And then you multiply this negative 1 by the negative 2 on the upper left, you get positive 2. And then you add 2 with 2, you get 4. And then multiply 4 by negative 2, you get negative 8. And then finally you add negative 2 with negative 8, you get negative 10. So it's multiply up, add down again, right? So So we got the quotient, and we got the remainder for this division. And so, as we said before, the remainder for this division is the number at the bottom row. So that's negative 10. So this is the result we got from the syntactic division. We can also find the remainder of this division by plugging -2 for x in the dividend p. So if you do that, you're going to get p of -2 equals 2 times -2 cubed plus 3 times -2 squared plus 2 times -2 minus 2. So -2 cubed is -8. So you get 2 times -8 in the first place. -2 squared is 4, so you get 3 times 4 in the second term. And then 2 times -2 is -4, so that's the third term. And then you subtract 2. So 2 times -8 is -16. 3 times 4 is 12. So -16 plus 12 is -4. -4 plus -4 is -8, and -8 minus 2 is 10. So we just evaluate the polynomial at x equal to -2, and we got that equal to -10, which is the same as the remainder of the division by the polynomial divided by x plus 2. Okay, so that's a verify the theorem. If you divide the polynomial p by x minus c, so in here c is -2. If we divide by x plus 2, then the remainder equals p of c, which is p of -2 in here. And we do have the same remainder -10 in both ways, right? So let's just check the other division. So this time we need to divide the polynomial by x minus half. So again, write the coefficients 2, 3, 2, -2 of the dividend, and then put a half side on the left, separate by a vertical bar. Again, you want to put 1/2 instead of -half because we are talking about division by x minus c, so c is equal to half in here. Okay. You can always use syntactic division whether this c is positive or negative, or fractional, rational numbers, or even complex numbers, anything, irrational numbers. You can always use the syntactic division. So let's just do it for 1/2 in here. So the first step is moved down 2, okay? And then you multiply 2 by 1/2, you get 1. So you put that 1 under the 3, and you add 3 and 1, you get 4. So that's add down, and then you multiply 4 with half, you get 2. And you put 2 up, so multiply up under the 2 of the coefficient. And then you add 2 with 2, you get 4. And then you multiply half with 4, you get put the under -2, so you get -2 plus 2, you get 0. So in this syntactic division, px divided by x minus half, the remainder is 0. So according to the remainder theorem, we can also use the evaluation of this polynomial p at 1/2 to find the remainder. Okay. It says if polynomial p is divided by x minus c, so divided by x minus half in here, then the remainder equals p of c, or p of 1/2. So that means, excuse me, since we get 0 from the syntactic division, in here we should also get 0 if we plug in 1/2 for x in p. So let's just see that. Excuse me. So p of 1/2. So I'm plugging half with for x in the p. So you get 2 times 1/2 cube plus 3 times 1/2 square plus 2 times 1/2 minus 2. 1/2 cube. So you just multiply 1/2 by itself 3 times. So you're gonna get 1/8. 1/2 squared is 1/4. So then you just do this multiplication. So 2 times 1/8 is 1/4 if you simplify a little bit. 3 times 1/4 is 3/4. 2 times 1/2 is 1. So we get 1/4 plus 3/4, which is 1. And plus 1, so we get 2 minus 2 equal to 0. So we do get the P of 1/2 equal to 0, which is the same result as we got from the syntactic division. So these two examples just verify the remainder theorem, okay? So we have two different ways to find the remainder of this division by x minus c. All right? Any questions at this point? No question. So you should be familiar with syntactic division. You should do syntactic division practice by yourself. Okay, so the next theme we discuss is called the factor theme. It says a polynomial p has a factor x minus c if and only if p of c equal to 0. Okay. So if you got the remainder equal to 0, obviously x minus c is a factor, right? Because you only get a quotient. There's no remainder. Okay. Everything is just cleared up. So that means x minus c is a factor of p if and only if c is a 0 of p. Okay. So what does it mean by a 0 of p? It means if you plug in that number c for x in p, you get 0. Okay, so that means p of c equal to 0. All right. Okay, so these are different languages, different phrasing of the same fact. So let's just use the factor theme and do a couple of examples. As here we have a polynomial p equals x to the fourth plus x cubed minus 21x squared minus x plus 20. And we want to know whether x plus 5 and x minus 2 factors of px. Okay, so we can do syntactic division. Okay. Because what, if you get 0 in the remainder, then that means it is indeed a factor of px, right? Okay. So let's just do the syntactic division. So x to the fourth, coefficient is 1 cubed, coefficient is 1. Negative 21x squared, the coefficient is negative 21. Negative x, the coefficient is negative 1. And a 20 in here. And then if we do the syntactic division by x plus 5, so you're going to put the negative 5 outside on the left. So in the first step, you just move 1 down and multiply 1 with negative 5, you get negative 5, and put it in, under 1. So then you add 1 with negative 5, you get negative 4. And then you multiply negative 4 with negative 5, you get positive 20, and put it down negative 21, and add negative 21 with 20, you get negative 1. And then you multiply negative 1 with negative 5, you get positive 5, and put it under negative 1. And then add negative 1 with 5, we get a 4. And then multiply 4 with negative 5, you get negative 20. And put that down, below 20. So you add 20 with negative 20, you get 0. So we do get 0 remaining here, or p of negative 5 equal to 0, right? So that means x plus 5 is indeed a factor of p. Okay. How about the x minus 2? So we just do syntactic division with x minus 2. So you're going to put the 2 outside instead of negative 5, and then see what happens. Move down 1, and then multiply 1 with 2, you get 2. put it down the 1. So then you get 1 plus 2, you get 3. 3 times 2, you get 6. Put it down negative 21. And then you add negative 21 with 6, you get negative 15. Multiply negative 15 by 2, you get negative 30. Put that down to negative 1. Add negative 1 with negative 30, you get negative 31. And then you multiply negative 31 with 2, you get negative 62. So put it under 20, you add 20 with negative 62, you get a negative 42. So this time you don't get a 0 for the remainder. So that means x minus 2 is not a factor of the polynomial p, right? Or you can say p of 2 is not a 0, okay? Any questions? No question. Let's go to the next page. Okay, and the next thing we talk about is called the reduced polynomial. When you divide a polynomial by another polynomial, you get a quotient. If you get a 0 for the remainder, okay, that actually means you factor the polynomial, the dividend. And what you get, in the factorization, is called reduced polynomial. So let's just do one example of reduced polynomial. So we have a polynomial p equals 2x cubed minus 3x squared minus 4x minus 15. And we want to know whether x minus 3 is a factor of p or not. So again, just do a syntactic division with 3. Okay, so I put all the coefficients of the dividend, the p, we get a 2, negative 3, negative 4, and then negative 15. As we know, if there's any term missing in this polynomial, then you need to put a 0, right? So we don't have any missing terms, so we don't have to worry about it. Okay, so move down to multiply 2 by 3 get 6, and then put 6 down, negative 3. Add negative 3 with 6, you get 3, and then multiply 3 with 3, you get 9. Put 9 on the negative 4, and add negative 4 with 9, we get 5. And multiply 5 with 3, we get 15. Now put down under the negative 15, and then add negative 15 with 15, we get 0. So we get the remainder 0. So that means x minus 3 is indeed a factor of p. Okay, and then we can easily write down this division by p equals x minus 3 times 2x squared plus 3x plus 5. Remember, excuse me, the last number on the bottom row of syntactic division, which is 0 in here, is the remainder. So we get no remainder, and other numbers are the coefficients of the quotient. So you divide x cubed minus 3x squared minus 4x minus 15 by x minus 3. So the highest power of the dividend is x cubed. So when you divide it, you should get a x squared as the leading term in the quotient. So the quotient will be 2x squared plus 3x plus 5. So again, you can rewrite this division by p equals the divisor x minus 3 times the quotient, the 2x squared plus 3x plus 5. All right? And because there's no remainder. And then this 2x squared plus 3x plus 5 is called the reduced polynomial from the original polynomial p. Okay, so you just reduced the power from 3 to 2 by factoring p, right? Any questions for this example? All right, no question. We just go to the next section. 3.2, let's see what we have in here. Looks like we're going to have okay, 8 pages. I don't know if we can finish or not today. So 3.2 is called polynomial functions of higher degree. We're going to discuss a few things about polynomials with higher degrees. Okay, so let's just assume you have a polynomial p in general with highest power n. Then you can write the polynomial as an times x to the n plus an 1 times x to the n minus 1 plus all the terms down to x1, x plus x0. Okay, so we got all the terms with the power of x up to n here. And those an minus 1, a1, a0, those are called the coefficients, as we know. So let's just talk about the forward left and forward right behavior. We want to know what it looks like. If you draw the graph of P, what does the graph look like on the forward left or forward right? And there are only, 4 different cases. On each side, either forward left or forward right, the curve can go up or go down. It cannot be flattened because it is polynomial. So it either goes up or goes down on the left and on the right. And then you have 4 combinations for those behaviors on the left and right. And the first combination or the first case is the graph of polynomial p goes up both on the upper left and upper right. And this happens when the highest power n, we call it degree, is even, and the coefficient for the leading term x to the n is positive. Okay, so like 1 times x to the 4th, and we got other terms. Then you don't have to worry about all the other terms. The curve has to go up both on the left and on the right. Okay. When n is negative and the highest power n is even, then both the curve goes down on both ways, up, left, and right. Like -2 to the 6 as the leading term plus all the other terms. Then you don't have to worry about the other terms, and this curve will go down on both ways because the leading coefficient is -2 and the n is 6. It's even. Okay, so that's the case when n is even. When the highest power n is odd, then the curve will go up on one way and go down on the other way. So when the leading coefficient, the an, is positive, and the coefficient for the highest power term, like 3x to the 5. Okay, so an is 3 and it's positive. the highest power is 5. And again, you don't have to worry about all the other terms. Lower than that, and the curve has to go down on the left and go up on the right. Okay. On the other hand, if n is -1 and n is odd, like negative 4x cubed, for example, as the leading term, then I have to worry about the other terms. This time n is -4, and n is odd, is 3. And this time the curve will go up on the left and go down on the right. Okay, so why do we want to discuss this behavior? Because in many cases, you want to sketch the graph of a polynomial, by hand. If you don't have the computer, you only have a pencil. pen and the paper, how do you sketch the polynomial? And then you want to see how the curve looks like on the far left and on the far right, and then you can also determine how many variations of the curve in between. But it will be much helpful if you know the far left and far right behavior of the curve. Okay, so you know how it goes on the left and on the right, and then you just figure out the curve in between, right? Okay, so that's the first thing. So let's talk about a few examples by using these rules. So let's just determine the far left and far right behavior of the polynomial p equals x cubed minus x. So again, you just look at the highest power term x cubed, and the power n is 3, so that's odd, and the coefficient of x cubed is 1, so it's positive. So according to the rule, when n is positive and n is odd, it will go down on the left and go up on the right. Okay, and indeed that's the case. If you draw the curve, you get something like this. Okay, as shown on the right. Okay, how about the other polynomial s equals 1/2 x to the fourth minus 5 over 2x squared plus 2. So this time it has the term is 4x to the fourth. So the exponent, the 4 is even, and the coefficient, the half, is positive. So according to the rule, when the coefficient that has the power is positive and the highest power is even, then the curve goes up both on the left and on the right, right? So if you draw it, you do get it, that behavior. So you can see the graph on the right, it goes up on both ways. Okay, any questions? No question. Let's go to a couple more examples. This time we got another polynomial t equals negative 2x cubed plus x squared plus 7x minus 6. So again, we just look at the highest power term, negative 2x cubed, and the exponent, the 3 is odd, and the coefficient of this term is negative 2, so that's negative. And so when the leading coefficient is negative and the power is odd, then the curve will go up on the left and go down on the right. Okay. So the curve is shown on the right side. You can see that's indeed the case. Let's do one more example. If we have a polynomial s equal to 9 plus 8x squared minus x to the fourth. Okay. So you look at the highest power, okay? So you don't look at 9, you look at negative x to the fourth, okay? So this polynomial is not really in the descending power. So you have to look at the highest power, x to the fourth. So it's even. The coefficient, the exponent 4 is even, and the coefficient for that term is negative 1. Okay, negative x to the fourth. So that's negative. The power is even and the leading coefficient is negative, then the curve goes down both ways. And that's indeed the case if you look at the graph on the right. Okay. So without using a computer, you can scratch the graph a little bit. Okay, let's talk about maximum minimum values of a function or a curve. So on the right side, you see a curve. It has several points, low and maximum and minimum points on the curve. Okay, we have 5 points in here. We can discuss the maximum and the minimum, and we can characterize the minimum or maximum into different types. One type is called the absolute minimum or absolute maximum. Or sometimes they're called the global minimum or global maximum. That's the highest or lowest point on the whole curve. So if you look at the curve on the right, there is indeed a lowest point on the whole curve. That's E with x5, y5 as the coordinates. So there is an absolute or global minimum for this polynomial or curve. And there's no absolute or global maximum because this curve goes up or both ways, without bound. Okay. And then we got 4 other maximum minimum points, A, B, C, and D. They are called relative or local minimum and relative or local maximum. For example, A and C, those are 2 minimum points, but they are local minimum or relative minimum because they are the lowest points locally, but not the lowest point on the whole curve. Okay. Similarly, B and D, and they are relative or local maxima, because there are maximum points locally, but not the maximum point on the whole curve. Okay, so we got them relative or local maximum. All right, so these are just some definitions. Okay, the next thing we want to talk about is the real zeros of a polynomial function. As we talked about before, what does it mean by real zeros of a polynomial function? It means when you try to solve a polynomial equation, the solutions of the equation are called the zeros of a polynomial. Real zero means all the real solutions for this polynomial equation. Okay, so real zeros of a polynomial function is the real solutions of a polynomial equation. Okay, so for example, if we want to find all real zeros of the polynomial p equals x cubed plus 3x squared minus 4x, it is asking you to solve this polynomial equation x cubed plus 3x squared minus 4x equal to 0. Okay, that's the actual question. So we know how to solve it. We just factor it. So first you can factor x from the left side. You get x squared plus 3x minus 4, and then you can further factor x squared plus 3x minus 4 as x plus 4 and x minus 1. So you got 3 factors in here, x plus 4, x minus 1, and you set each of those factors equal to 0 and solve it. You got 3 solutions, x equal to 0 for the first factor, x plus 4 equal to 0, you get x equal to negative 4, x minus equal to 0, you get x equal to 1. So you got 3 solutions to this polynomial equation, or you can say there are 3 real zeros of this polynomial function. Okay. So this again is just another way to say solutions for equation. Okay.